Question 8, part B, we're asked to use mathematical induction to prove that 2 to the power of n plus 1 is greater than n squared, where n is an integer and n is greater than or equal to 3. So when we want to prove something by mathematical induction, the first thing we have to do is prove that the base case is true. So for our problem here, that is when n is equal to 3. So for our base case, which we have n is equal to 3, well then we get 2 to the power of 3 plus 1 is equal to 2 to the power of 4, which equals 16, and that is greater than 3 squared, which is equal to 9. So we can say that our statement is true for n equals 3. So we can just write so, true for n equals 3. Now the next step is we have our hypothesis statement. So we assume our statement that we want to prove is true for n equals k. So we can write assume true for n equals k. And I'll just make clear that k is an integer and k is greater than or equal to 3. So the statement that we're assuming is true is 2 to the power of k plus 1 is greater than k squared. So I'll make that clear also. So we go, that is, assume that 2 to the power of k plus 1 is greater than k squared. And so the next step we do is we want to show that if it is true for n equals k, then it is also true for n equals k plus 1. So for n equals k plus 1, we want to think what we want to end up with. So we have our statement, 2 to the power of n plus 1 is greater than n squared. So if we have n equal to k plus 1, we want to end up with something like this, 2 to the power of k plus 1, so I'll put that in brackets to make it clear, plus 1 is greater than k plus 1 all squared. So what we'll do now is we'll plug k plus 1 into the left hand side of our statement there and see if we can end up with this. See if we can show that 2 to the power of k plus 1 is greater than k plus 1 all squared. So plugging in n equals k plus 1, we're going to get 2 to the power of k plus 1. Well, that is equal to 2 times 2 to the power of k plus 1. And that is going to be greater than 2 times k squared. And that is just from our hypothesis statement down here, where we have assumed that 2 to the power of k plus 1 is greater than k squared. So we can write that in. We can say as 2 to the power of k plus 1 is greater than k squared. And we can write 2 times k squared as k squared plus k squared. And we know that that is going to be greater than k squared plus 2k plus 1. And we know that from part A, because we had this inequality here, x squared is greater than 2x plus 1. And we know that is true if x is greater than 2.41. And we're assuming here that k is greater than or equal to 3. So we can definitely say that k squared is going to be greater than 2k plus 1. So now we just factorize that statement there, k squared plus 2k plus 1. So that's going to be equal to k plus 1 all squared. So now if we follow our inequality through here, we've got 2 to the k plus 1, and that is greater than k plus 1 all squared. So therefore, we have 2, and I'll just put the k plus 1 in brackets to make it clear. K plus 1 is greater than k plus 1 all squared. So we have shown that if our statement is true for n equals k, then it is also true for n equals k plus 1. And as it's true for when n was equal to 3, then our statement 2 to the power of n plus 1 is greater than n squared is true for all n greater than or equal to 3 by induction, where n is an integer. So we'll just note that down. So the key parts of the statement are, if we've assumed it's true for n equals k, then it was true for n equals k plus 1, and as we've proven the base case, it was true for n equals 3, then it was true for all n greater than or equal to 3. Okay, and that is question 8, part B.